This is the second video for section 2.8, and this is going to be limits involving infinity. So as a sort of motivating example for some of the concepts we're going to consider in this part of the section, let's consider the function y equals 1 over x. So as you know, that function has this graph pictured here. And let's consider what's happening to this function as x goes to 0 from the right. So as x goes to 0 from the right, what's happening to the y values? Well, they're growing without bound. So we might say that the limit as x goes to 0 from the right of 1 over x equals infinity. Now we know that means that the limit doesn't exist, but we can say in what way it doesn't exist. Namely, those y values blow up. Now, similarly, if we look at the limit as x goes to 0 from the left, what's happening to the y values? Well, they're going down to minus infinity. So they're blowing up, but they're blowing up in the negative direction. This is what we mean when we say y equals 1 over x has a vertical asymptote at x equals 0. So you might draw that in with a dotted vertical line. But by definition, what it means to have a vertical asymptote is that the limit on either side is either positive or negative infinity. On the other hand, what's happening to this function 1 over x as x goes to infinity? So as x gets really big, what's happening to the graph of 1 over x? Well, it's going to 0. So what we mean by that is that the function 1 over x has a horizontal asymptote, which we might put dotted horizontal lines there at the line y equals 0. So what about the function arctangent of x? What happens when we take the limit as x goes to infinity of that function? Well, the graph of arctangent, as you know, looks like this. It's sandwiched between negative pi over 2 and pi over 2. And so as x goes to infinity, the y values on arctangent are getting closer and closer to pi over 2. But as x goes to negative infinity, the y values on arctangent are getting closer and closer to negative pi over 2. So we would say that arctangent has a horizontal asymptote at both y equals pi over 2 and at y equals minus pi over 2. So between these two functions, 1 over x and arctangent of x, we've seen two different scenarios. Either we can have a single horizontal asymptote, like y equals 0 for the function 1 over x, or we could have two horizontal asymptotes, as in the case of arctangent. So let's make this asymptote business a little bit more precise. By definition, we say that if we take the limit as x goes to infinity of f of x and we get a number L, and or we take the limit as x goes to minus infinity of f of x and we get a number L, then we say that f of x has a horizontal asymptote at y equals L. And horizontal asymptotes are important because they govern the end behavior of functions. So they tell us as x gets really, really big, or as x gets very, very negative, is the function approaching some fixed horizontal line. That's what horizontal asymptotes tell us. On the other hand, vertical asymptotes tell us about places where functions are undefined, and they tell us about in what way are functions undefined. So if the limit as x goes to a of f of x is either plus or minus infinity, then we say f of x has a vertical asymptote at x equals a. So that's why we said that 1 over x had a vertical asymptote at x equals 0. Another thing that we can think about when we're thinking about limits involving infinity is we can think about the end behavior of rational functions. So in other words, we can think about the limit as x goes to infinity, or the limit as x goes to minus infinity, of p of x over q of x, where p and q are both polynomials. So remember, the ratio of two polynomials is called a rational function. So for example, let's say I wanted to know about the limit as x goes to infinity of x to the fifth minus 4x squared plus 7 over 3x to the fifth plus 1. So if we just sort of plugged in infinity, and I use that with great quotes, if we started plugging in big numbers for x, we would see both the numerator and the denominator of this function are getting bigger and bigger. So we would say that this limit has type infinity over infinity. And it turns out infinity over infinity is also an indeterminate form. It gives us no information about what the limit of the function may be. So it's another one of these cues to us that we need to do more work. And when it comes to having a rational function, we can do a cute little algebra trick. Namely, we can multiply the top and the bottom of our rational function by 1 over x to the highest power that appears anywhere in the function. So for example, in this case, we can take the limit as x goes to infinity of x to the fifth minus 4x squared plus 7 divided by 3x to the fifth plus 1. X to the fifth is the highest power that we see, so we multiply the top and bottom by 1 over x to the fifth. And then when I do that, I get the limit as x goes to infinity. I factor that 1 over x to the fifth through, and I get 1 minus 4x squared over x to the fifth plus 7 over x to the fifth. And in the bottom, I get 3 plus 1 over x to the fifth. Now, let's think about what is happening to these terms as x gets really big. Well, 1 and 3, they don't have x's in them, so they're not going to go anywhere. But how about that negative 4x squared over x to the fifth? As x gets really big, x to the fifth is going to get bigger much faster than x squared. So that expression is going to go to 0. Similarly, if I take 7 and I start dividing it by something really big raised to the fifth power, then that is going to be getting smaller and smaller. So that's going to go to 0. And same argument, 1 over x to the fifth is going to get really small as x gets big, so that's going to go to 0. So what I'm going to be left with is the limit as x goes to infinity of 1/3. Well, there's no x in that expression, so that's just 1/3. So this limit as x goes to infinity of x to the fifth minus 4x squared plus 7 over 3x to the fifth plus 1 is equal to 1/3. So that algebra trick is all well and good, but what if I wanted to know about the limit as x goes to infinity of x squared over e to the x? Well, this is also type infinity over infinity, but your algebra trick doesn't work here because I don't have polynomials, I have one polynomial, I don't have two polynomials, so I don't have a quote-unquote highest power, highest order term that appears. So we need some other way to handle this, and I will ask you to stay tuned to class. We'll talk about a version of L'Hopital's rule that works for the case of infinity over infinity.